far talked about like raising a variable to a power or a number to a power. Now we're going to talk about what happens when your variable is the power. So we're going to look at things that have a variable in the exponent, like this. And we're going to figure out what this does, what it looks like, what values it can have. How do we solve for this? How do we get it out of there? That's our vision for this unit, okay? So exponentials is what we're going to look at first. And then also today and kind of the rest of the unit, we're going to look at logarithms, which is going to help us get the x out of the exponent, okay? Before we do any of that, we got to talk about graphing really quick. Do we remember what an asymptote was?
The line that it like gets close to?
Yes, it's like those dashed lines that we drew that our graph gets really, really, really close to, but it never actually hits. It can never actually be that value. So we're going to go through these 4 graphs to figure out what the asymptote is and the domain and range, because these are the type of graphs that we're going to be working with this unit. Let's start with the asymptote. The red line here, if we use Hoy-Vux, is that a y equals or an x equals? Hoy, y equals. Y equals, and what value is that at? -1. So y equals -1. And then if we start talking about domain and range, which we haven't actually had to look at in a while, but for domain, that's my x values. If I'm over here on the left at -infinity, do I have points over here? Yeah, my arrow's pointed in that direction. Following through, do I have points all the way to infinity? Yes. So domain, all real numbers, or -infinity to infinity. My range is what's a little tricky. Where do my points start? -1. I don't have anything beneath that. Is -1 included?
Yes.
Do I have points on this red dashed line? No. That was my asymptote, right? And it can never hit that line. So -1 is not included. We use parentheses. And then do I have points all the way through to infinity? Yes. To infinity. Okay. Yeah.
So like, is it not symmetrical?
What do you mean?
Because like, if the lower line doesn't go anywhere beneath the asymptote, but the...
Correct. You're right. Yes. It's not symmetrical. Okay. There's no, like, this curve here. You can't just flip it on itself.
Okay, so this one kind of stays like straight.
Super flat right here, and then it takes forever to get high up there, but yeah.
Okay.
Or no, sorry, it takes a really short time to get up there. When we are at like 5, it's going to be like in 1,000.
Yeah.
So like it's going to get up really, really fast.
But not over.
But it's never going to go down.
Okay.
But this way it's going to shoot up really, really fast. And we'll talk about that more when we look at what the actual points are. Great question. Ready for another? Let's hop over to the right-hand side. This one's a little bit different. My asymptote, if we use Hoy-Vux, is this Hoy or Vux? Vux, it's vertical. Vertical, so it's x equals what? 0, right, on the x-axis, or the y-axis. Domain, starting all the way at -infinity. Do I have points at -infinity? Yes, my arrow's pointed to the left, right? When do my x values stop?
At 0?
At 0. Is 0 included or excluded?
Excluded.
It's excluded. That's where my asymptote was, right? So we're going to go -infinity to 0, excluded. So with parentheses. What about range starting at -infinity? Do I have points? Yep. To infinity? Yep. All real numbers. Boom. I want you guys to take 2 minutes to try to do the bottom 2, just to kind of refresh yourself on domain and range a little bit.
How do we know which one is the one that gets close to the asymptote? Is it the long
It's just the one that is approaching, like here's your dash line. This arrow's closest to that dash line, so it's this one.
Oh, I didn't see the dash.
Yeah, the dash lines are hard to see a little bit, so Oh, that's not your dashed line, Ava.
Oh,
Never mind.
that's why I was
Look
like,
at my screen if you cannot see your dashed lines on your paper. It printed weird. Look at the red lines on my screen and just make them bold on your paper so you can see it a little better. And we'll go over these in a second. Good, very good.
So if the asymptote is horizontal, we do Hoy.
Mhm.
If it's vertical, we do Vux.
Yes. You guys learned Hoivux in Algebra 1, right? Okay. I didn't think I introduced that to you, but. How we doing back here, AJ?
Wait, so we're following like Hoivux, right? So since this is like vertical, it's gonna be like, it's gonna be x, right?
And then where is that line? Like here's -2, here's 2. What's in between those?
A 0.
0. Perfect. So x equals 0. Careful on that one. Look at my screen for a second. It's really hard to see. Do you see that red horizontal line?
Oh yeah.
It's horizontal. Is that Hoy or Vux? No, the wind is just blowing it. It's just blowing it.
Is it just gonna be
Well,
this number is?
hold on. It's horizontal. So is that Hoy or Vux?
Oh, it's Hoi.
Hoy. So is it X or Y? Y. So I want you to think vertically. Where is that line? Well, if you look at my screen or at my iPad here, here's 0. Here's 2. What's in between them?
0.
Between 0 and 2?
Oh, 1.
1. So try that
so
for your asymptote. There you go. Shall be good. All right, let's talk about these. This red line, it's horizontal. Hoy or Vux? Horizontal? Hoy, okay. So it's y equals. And then if we just make our way up the y-axis, what y value is this? 1. Perfect. Domain and range. Do I have points for domain at -infinity? Yep. Do they ever stop? No. It looks like they almost stop at 0, right? There's no dashed line there, so they don't. It's just like super low. Like if we graphed this, we'd have a point like way down here. So it just falls off our graph really fast. It's exponential. It gets really, really big, really, really fast. Okay. So domain, -infinity, and it doesn't stop to infinity. Range. Do I have points down here at -infinity? Yes. When do they stop? At 1, excluded because of the dashed line. And then the other side for our asymptote, is that Hoy or Vux? Vux. It's vertical. So it's x equals. Really hard to see on your paper, but what x value is that? It's between -2 and 2, right? 0. It's right in between those. It's 0. It's right on that y-axis. Domain. Oh, Avery.
So whichever one the asymptote one is like the same thing in like either like domain or range. Like the asymptote is like okay.
Yeah. Do you want to keep going, or do you want me to try to?
You can probably.
Okay. So what Avery's saying there is she's like, okay, there's a -1 here in my asymptote. That's going to show up in my domain and range somewhere. And she's right, it is. And how it actually works is you realize how y values go with our range. That's the one that it's going to show up in. Whatever x or y, whatever you see up here, associate that with your domain and range, and that's where it's going to show up. So you're spot on, Avery. Over here, we have x equals something for our asymptote. So that something, that number is going to show up in our domain for our x's. Great observation. Anything else before we do this guy? Okay, domain. Where do I start my x values? 0. Again, that number's going to show up in my domain, right? So 0. When do they stop? Infinity. Range. Are there any values that my function can't have? Are there any restrictions on y? No. All real numbers there. -infinity to infinity. And what these graphs are actually the two graphs that we're going to graph, the two functions that we're going to graph in this unit. This first one on the left, those are exponential functions. This is what we're going to graph today. What type of asymptote do exponential functions have just based on these two examples? Horizontal or vertical? Horizontal. So horizontal asymptote. Notice how these graphs look very similar, okay? They're going to be two completely different functions, though. This one on the right-hand side is actually going to be the inverse of the exponential function, which we'll talk about today, but you guys will graph on Monday, okay? We call that a logarithm or a logarithmic. We'll get into it in the second lesson here. The difference in the graphs is essentially a horizontal versus a vertical asymptote. The difference in the functions is your exponential, something like this, is your variable is in the exponent. So say our exponent here was 3. What would 2 to the third be? 8. If we do a logarithm, our logarithmic function is only going to have the 2 and the 8, and it's going to take the x out of the exponent. And I did a terrible job at explaining that, but I promise we're going to get to it in the next section. Let's just graph exponentials. We're not even going to hop into logs right now yet. Okay? Is that okay with everyone? Okay, we're going to get to it in a second. But let's graph exponentials first. So again, the key is that the variable's in the exponent. That x is a power. When we talk about exponentials, the number that's raised to a power, we're going to call that the base. So b is the the A value in the front, usually stretches or shrinks our graph, okay? And one restriction that we have on our base here is that we're never going to have that base be a negative number. Because let's think about what happens. If this is negative 2, what's negative 2 to the first? Negative 2. What's negative 2 to the negative first?
2.
Fraction, right? But what's negative 2 squared? 4. So this graph is going to hop back and forth between negative and positive numbers. Negative 2 to the first is a negative number. Squared is a positive number. Cubed is a negative. So it's going to look like this, where you have points on both sides of that axis. We're not going to graph those, okay? So for our purposes, b is always going to be positive. It's a positive number. So if you see a negative, that negative is attached to not your base, it's attached to the number out front. We're never going to raise a negative number to a power in this unit for now. Okay? Depending on what b is, it determines whether our graph is growing or decaying. Essentially, is it getting faster and faster and faster, or slower and slower and slower? Okay? If b is a fraction greater than 1, it's exponential growth. What this means is our graph is getting farther and farther away from the asymptote. So it moves away from the asymptote. So if we look up here, and I don't want us to think of growth and decay as positive and negative, because that's not necessarily what it is. That's our A value is going to determine like going down or going up. But the B is going to determine how fast our graph does that, okay? If we look here, is this line moving closer to our asymptote as we go towards infinity or farther away? Farther away. Even though it's going down, this is still exponential growth. The base is still going to be greater than 1, okay? We're getting fast, like farther and farther away. We're growing faster. The difference between these two is a lot less than the difference between these two. So we're getting faster and faster and faster, steeper, okay? That's growth. Decay will do the opposite. So that's when our base is less than 1. It's a fraction. Again, not negative. We're all positive here. And it'll move closer to the asymptote. So what we're first going to do is just look at a few functions and see if they're growth or decay. If you have like a highlighter colored pencil, or if you want a marker, some are backed by Jackson, I'm going to just like highlight what the base is for each of these just so we can see it, and then I'll write down growth or decay. Okay? So there's markers behind Jackson if you need them. But what we're looking for here is what is the number raised to a power. So if we look at this first one, what number is being raised to the x plus 2 power? What number? Sorry, I'll give you guys a second. Is it -5 or +5? Positive. It's always positive. So our base here is positive 5.25. Is that bigger than 1 or less than 1? Bigger. Growth or decay? Growth. Bigger than 1 is growth. So our base is 5.25. It's growth. Next one, and again, we might not just have an x in the exponent. There might be some other things going on. But what number is being raised to a power in this next one? 0.75. Less than 1 or greater than 1? Less. Growth or decay? Decay, because it's less than 1. Next one, we're getting an a value in there, but what number is being raised to a power? 3.1. That's greater than 1, so it's growth. Next one, what's the base of that bottom left function?
Like the 1/3.
1/3, that's what's being raised to a power. The 4.25 is essentially how much it's going to stretch or shrink. It's a scale factor. 1/3, greater than 1 or less than 1? Less. Growth or decay? Decay. Are we keeping up with our colors? It's really easy for me to switch, but it might not be easy for you. Good? Okay. Next one, what is being raised to the x plus 1 power? 5. That's greater than 1. Growth or decay? Growth. Last one, possibly the trickiest. 4/3 is our base. That's a fraction, but is it a fraction greater than 1? Yes. So it's still bigger than 1. Growth or decay? Growth. So just because you see that fraction does not necessarily mean decay automatically. Okay? So just be a little bit careful on that. Question? Yeah, May.
Yeah, I'm confused why the first one is
Growth. So we always take the positive. Notice how the negative's not in parentheses. So it's not being raised to a power. It's just the 5.25. So that's why it's still bigger than 1. Great question. What the negative is going to do is just flip it. Okay. Questions on those, growth versus decay. Okay. Here are the parent functions for growth. And a reminder that both of these can be flipped at any point with that a value. So it could look like this where it's truly growing, or if we just have a negative version, it could look like this. Okay, so growth doesn't necessarily mean getting taller. It means as we move along, we're just getting faster. The slope, or the relative slope in between 2 points, is getting bigger. If we look at decay, from left to right, this slope, if we made a straight line and estimated a slope, it would be super steep, right? But as we get farther and farther, our slope gets smaller and smaller. Doesn't necessarily have to go down. If we flip it, it would look like this. But again, it's loading. Our slope here, steep, and as we move, it gets less and less steep. Does that make sense? Growth versus decay and what that means graphically. All of that, though, will come from your table. So when you graph this, you don't actually have to think about, is it getting steeper or is it not? Zayna, you sure?
Yeah.
Okay. For all of these, we kind of already talked about it, but there's going to be a horizontal asymptote, and that's going to show up in our range. So for our parent function, the horizontal asymptote is at y equals 0. So that means our range is 0 to infinity. Or if we flipped it, like these purple ones, negative infinity to 0, it would flip our range as well. And then domain, can we plug anything into an exponent, any number? Are there any restrictions horizontally? No, it's all real numbers, always, for exponential functions. So, let's graph them. And I have a bunch of examples on here. I don't think we're going to do all of them. We're definitely not going to do all of them. We're going to do 2 basic ones, probably 4 basic ones, and then we're going to do some transformations. So next page, how are we looking on time? Perfect. Okay. We're going to graph these, and we're going to graph them using a table. What would be, let's just think about this, what would be the easiest numbers to plug into x? What are they? 1 is easy, what else? 2, 0 is really easy. Probably like a -1 to 1 situation. Centered around the origin makes it easiest. So let's just plug in 3 points. Eventually I'm going to let you only plug in 2. So we're doing a lot right now versus what we're going to do on the next page. So if I plug in -1, 0, and 1, this is raising 2 to the negative first power. What does a negative exponent do? Fraction. Not a negative number. It hurt my soul on some of our tests. Speaking of, your tests are graded. They're in the grade book. Not everyone has finished it or taken it, or they were absent. And we don't have ACLAB on Friday. And I'm not here on Monday. So it'll probably be till Thursday that you will see them. But they're in the grade book. You can let me know individually if you have some questions. Anyways, 2 to the negative first would be 1/2. 2 to the 0th, anything to the 0th power is what? 1. I'm just going to highlight that. This point is going to show up in every graph that does not have a transformation. And we'll talk about transformations in a second. But this would show up in like all of our parent graphs, no matter what base we have. Okay? And then what's 2 to the first? 2. And it's going to have a horizontal asymptote because it's exponential. So it's going to be at y equals 0. We're not moving up or down or anything. And then we can graph them. -1, 1/2 is like right here. 0, 1, 1, 2. And you could do a little bit more if you wanted. 2, 4 would be a point. 2 to the second is 4. And then 2 to the third is 8. So you could do a little bit more if you wanted once it loads up here. But 3 is fine for me. Okay. Connect your points with a smooth curve, getting closer and closer to that dashed line. Carolyn, did you have a question?
How'd you figure out where the asymptote?
We have not had a transformation yet, so it is the same place that these ones were at, because all that's changing is our base. This is just a b to the x function. It's just a parent function. We're gonna just change our base. So the parent function for this is just a little weird because our base could be anything. The parent function is a base of 2 or 3 or 4 or 5 or 1/2. Just depends. Okay, so we're not moving anything yet. It's still going to be y equals 0. Good question. Any other questions on that graph? Okay. Just thinking, if we plugged in 3 for our base, and we plugged in these same points, we would get 1/3, 1, and 3. And then we would get like 9. So as our base increases, it's going to get steeper and steeper. This graph right here, and we're not really going to make a table because of time purposes, but it would look something like this. And that is, you can't tell too much, but that is steeper than this. This has a point at 2.9, and this has a point at 3.8. This doesn't even get this high until 3. This one gets that high at 2. So as your base changes, that also changes the steepness of your graph. It essentially changes how fast you're going up. Same thing with that A value. It's going to stretch or shrink it. But that's kind of how those parent functions work. Questions so far? We're almost done with this section. Let's do one decay one, and then we'll be done. Let's do a decay with a negative and with a 3, because we did a positive 2 before. So let's hop over to the far right one over here. What's our base for this function? 1/3. Okay, that's decay. So that means eventually our slope should be getting like smaller and smaller. We should be scrunching the further to the right we go. Again, let's just plug in our 3 points. -1, 0, and 1. And then if we use reasoning and the logic that we all have, this negative number in front, what's it going to do to my graph? Flip it. So it's going to look like, in the long term, a decay function that's flipped. So it looks like this-ish. Okay? So going back down here, what is 1/3 to the negative first power? It's going to flip it. So the 3 is going to be on top, and it's to the first. So 3. And then that negative in front. So -3. So what I'll show my work here. I did negative 1/3 to the -1. Once it loads, so sorry. Goodness. 1/3 to the negative first was 3. And then we just put a negative on. So we get -3. Okay. And if we graph that, -1, -3 would be right there.
Can we plug that into our calculator?
Yes. You'll have a baby calculator though. So I'll have to see. I'm pretty sure there's an exponent button, but it wouldn't give, if you get any fractions, it would probably give you a decimal. But yes, final answer will be on Thursday when I see you. Hey.
So if the A value is negative, it's always going to be flipped?
Yes.
Even in like different units or?
Oh yeah, always,
Okay.
always, yep. Yeah. Okay, so this is our first point. Then we put in 0. What's anything raised to the 0th power? 1. And then we have a negative out in front. So -1. And then the last one, 1/3 to the first power is 1/3, and then we tack the negative on, -1/3. Again, our asymptote is y equals 0. And this one's decay. So notice, if we start on the left, my slope is really, really steep. But as we move farther and farther, my slope gets scrunched a little bit. It's less and less steep. Okay, questions on the parent function? All right, now we're going to get to graphing it the way that we're used to graphing with H's and K's and all of those like little handy-dandy things that we kind of have to memorize. First, growth or decay depends on your base. So if your base is greater than 1, it's growth. If it's less than 1, it's decay. So there will be like essentially it'll say growth or decay on like a test or homework, and you'll just circle one. So you will have to pick. And then your asymptote always comes from your H value. So this determines your horizontal asymptote, and it's at y equals, not H value, your K value. Y equals K. Because it's horizontal, and K goes with Y, and that's what we're used to. Y equals K. Let's talk about A, H, and K really quick. A would change the steepness, so it would stretch or shrink. Kind of on top of the base, because the base is also going to change the steepness a little bit and how fast it grows or decays. So A is stretch or shrink, and it could also flip it. So if there's a negative, it would reflect over the x-axis. Okay. What does H usually do? Up and down or left and right? Left and right. And again, H is inherently x minus H, so we flip the sign of what we see, and that's our H value. We're used to doing that. B is just our base. It's going to determine decay or growth. And then K is going to move us up or down, and it's going to determine our asymptote, y equals K. Okay. The y-intercept, to find it, we actually have to go